All right, so I finished my general announcements. Happily, every single person has made up the Chapter 6 test, so that answer key is available on Canvas. Students are encouraged to check that and check their answer key. Of course, making sure you're paying attention to the right version. Did you take version A or version B? Pay attention to that. And some of you may have had version A of the multiple choice versus version B of the free response, so you definitely want to pay attention to that as well. All right, today we're going to conclude our lecture on section 7.1. We're going to start with 7.1.8. This is really similar to 7.17. So to me, it's a great problem to start a Monday on because it's really similar to the very last thing you did in this room on Friday. Of course, the context is different. All right, here we go. So during the winter months, outside temperatures at the Starness's cabin in Colorado can stay well below freezing. That's 32 degrees Fahrenheit or 0 degrees centigrade for weeks at a time. To prevent the pipes from freezing, Mrs. Starn sets the thermostat to 50 degrees Fahrenheit. The manufacturer claims that the thermostat allows variation in home temperature, and that follows a normal distribution with standard deviation of 3 degrees. Before I keep reading, this is absolutely a real world thing that all of you future homeowners should be aware of, that pipes can freeze. A quick example of this would be my wife has a family member who owns a condo out in Ocean City. They are very generous with it and let us use it occasionally, but they have made it clear that when we leave, do not turn the central air off. Set it to 50 because they're not necessarily going to head back there at the end of the summer, and then it'll get into the winter months. And if the central air is totally off, the interior of the condo could reach below freezing, and then any water left over in the pipes could freeze and expand and destroy pipes. So definitely makes sense to want to just set your thermostat to 50 degrees as a nice minimum. To test this claim, Mrs. Starnes programs her digital thermostat to take a simple random sample of size 10 readings during a 24-hour period. Standard deviation of the results is S equals 5 degrees Fahrenheit. Before we actually get to this, let me make sure that people understand what this is actually saying. The idea is the company is basically saying that if you set your thermostat to 50 degrees and then you check the temperature throughout the day, it is normal for it to vary by as much as 3 degrees. That's a typical amount of deviation. So 68% of the time, even if you have it set to 50, 68% of the time, the temperature in your home will be between 47 and 53. 95% of the time, it'll be between 44 and 56. Anything lower than 44 or higher than 56 when you have it set to 50, that should be alarming to you. That should strike you as unusual. Now, that's a claim about how consistent and effective their system is. You set it to this temperature, it'll do a good job of sticking near that temperature. What Ms. Starnes did is she said, all right, let me test this. She set her thermostat to 50. She took 10 readings throughout the day, and she got a standard deviation for her sample of 5 degrees, which means she observed more variability in the temperature throughout the day than what the company claimed. Everybody got this? Okay, so it says identify the population parameter sample and statistics. So you are trying to represent the temperature within the home. The way in which she did that was not to take a census of the temperature every single moment of the entire day. Instead, she took 10 readings throughout the day. Now, the goal is to basically get an idea of what is the actual variation in home temperatures. Okay, notice the symbol sigma. We use that symbol to represent the correct value, the actual standard deviation. Now, the company claims the actual standard deviation is 3 degrees. In her sample, she got 5 degrees. And notice that we use the letter S to represent that. So S stands for the standard deviation that you observed within a sample. So not necessarily the right answer, but something you observed in practice. All right, so where we're going to head with this is the company claimed we have a certain level of consistency within 3 degrees. She observed within 5 degrees. So then the question becomes, is this company lying to me? Did I see something unusual enough to call them liars based on their claim? And that's kind of what this next display is going to get to. It says, suppose the thermostat works properly and the temperatures in the cabin vary according to a normal distribution with mean of 50 degrees and a standard deviation of 3 degrees. The dot plot shows the distribution of the sample standard deviation in 100 simulated simple random samples of size 10. So let's make sure that we understand what's going on. You have a device that you set to 50 degrees, and we're going to pretend that device absolutely has a spread of 3 degrees, that the company's claim is accurate. Well, then you take 10 measurements throughout the day, And you expect to see within those 10 temperatures, you expect to see a deviation of about 3 degrees. Now, occasionally, and just by random chance, it'll be lower or higher. Please notice that all of the dots that are under what you expect, what those dots represent, are times when the temperature in the house was varying less than what the company claimed, that the houses were actually being more consistent than what the company claimed. Any dots above represent samples where the variation you saw in the household temperature throughout the day varied more than what the company claimed. That's what those dots represent. Okay. So if the company truly is telling the truth, you should see around 3 degrees. And that's why the simulated results are centered on 3, because the simulation was built on the assumption that the company is telling the truth. Okay. Now, this says, would it be unusual to get a sample standard deviation of 5 or higher in a sample of size 10 when the standard deviation is 3? Or to put it another way, the fact that Mrs. Starnes got 5 degrees of spread, according to these simulated results, was that unusual? Absolutely, because it never happened. What these simulated results are showing is that if the company is telling the truth, you should never see a spread of 5 degrees. So the fact that she did is definitely unusual. Okay, and that's sort of the answer to this question. You're asked, does this seem unusual? Okay, so I would just take note of the fact, not that you have to draw that box or anything, but that's just what I noticed, that we never saw deviations this far above. So I said, yes, based on the simulated results above, this would never happen purely by chance. Now, forgive me for, going back to the coin example. I like to do that a lot because to me it's a pretty intuitive thing. But let's just be clear on what's going on here. Pretend this was a simulated sample of what a fair coin should be. So imagine this is centered on 50% heads. Okay. So you flip a coin a bunch of times and you expect to get 50% heads. Sometimes you get less than 50%. Sometimes you get more than 50%. And so I pick up a coin and I'm like, I wonder, is this thing fair? I wonder, is this a fair coin? I have a picture of how a fair coin might behave by chance. Yes, it should be around 50% most of the time, but sometimes less, sometimes more. Now, I pick up that coin, I flip it, say 100 times, and I get 85 heads, which is somewhere over here, which my simulated results say a fair coin would never act that way. And so my reaction to this coin that I was just testing is, okay, it could be a fair coin. Like, I'm not going to lie, like a fair coin could have done that. But according to my simulated results, that should basically never happen. So the fact that it did, I suspect this coin is not a fair coin. I suspect it's biased towards heads. Okay, that's kind of what's going on here, except now we're talking about a company's claim regarding the consistency of a thermostat. Okay, and that's where we get to here. Based on your answer to part B, is there convincing evidence that the thermostat is more variable than the manufacturer claims? Absolutely. And then I provide some fancy notation, but it's really not that bad. Remember that S is a reference to a sample spread, a sample standard deviation. So I said yes, because the probability that a sample's spread is greater than or equal to 5, which is what Ms. Starnes saw, is 0%, meaning it's less than 5%. So this typically does not happen due to random chance. I will admit that parts B and C can feel almost like the exact same question. So just to kind of break those down a little bit, part B says, Miss Starnes got 5 degrees. Is that weird? The answer is yes, it's weird. The next part says, okay, well then, should you suspect the company is lying to you? And the answer is yes, I suspect the company is lying to me. So the two questions can feel almost redundant, but they're asking slightly different things. Questions? All right, so on the next page, I am not going to read through this whole page for you. I will encourage you, I would recommend that you read this on your own time. But I do want to comment on the images, the 4 bullseye images that you have, because this kind of talks about a very important distinction that we want to make sure we're making when we collect sample data. Okay, let me zoom in on this image for just a moment. Okay, so let's say I wanted to use my calculator to simulate flipping a coin 100 times. Okay, so that's going to look something like this. All right, so that's random int, zeros and ones, 100 of them, and then add them up. So I'm going to say zeros represents tails, ones represents heads. So that is, I just got, oh, right on the mark, 50 heads. How about this time? 41 heads. That's 9 off. Stop it. Why do it? Okay, that's kind of creepy. It's freaking me out a little bit. 51. All right, 51, 52. All right, I just wanted some variability here. That's all I was asking for. All right, so I mean, I did hit 53 of those times, but the other 5 times I didn't hit 50. I got 51, 52, 51, 45. The question is, why aren't I hitting 50 right now? Is there something inherently biased in the calculator where it's actively trying to avoid getting 50% heads? The answer to that question is, of course not. The reason I'm not hitting 50 on the money right now is something called natural variation, random chance. Okay. Now, you could be off the mark if you're doing something biased. Like if I'm flipping a coin and I'm trying to get it to land on heads and I actually have a technique where I could do that, well, then when I'm off the mark of 50% and I'm getting 62% heads, that's not natural variation, that's bias. And that's sort of what these 4 displays are trying to show you. In a perfect world, you would have an unbiased way of calculating data, so you're aiming at the right direction, and you'd be collecting a lot of data. So law of large numbers kicks in, and you're getting close to the real answer. Okay? Which of these images, 1, 2, 3, or 4, represent the ideal that I just referenced? You have an unbiased way of collecting data, and you're collecting a lot of it. Which of the images, 1, 2, 3, or 4, would represent that? Which one? Number 4. Number 4 would represent you are aiming in the right direction. You are hitting near the bullseye. Now, you're not getting it exactly. You're kind of pinging around the bullseye, but you're getting really close because you're collecting a lot of data. That's the ideal situation. Now, there are plenty of times in the real world where time, energy, money, size of the population just don't really allow you to collect a lot of data. And so you will hopefully at least be here. That is, you have an unbiased way of collecting data, so you are kind of fluctuating around the center, whatever the parameters you're trying to get, but you're not getting super close, not because of anything you're doing wrong, but because you're not collecting a lot of data. Okay? I could very quickly show you the distinction here by just going back to my calculator and saying, all right, we are 1% off, then 7% off, then right on the money, then 2% off. I want you to hear these numbers for a moment. 6% off, 3% off, 15% off. That's pretty unusual, actually. Right on the money, 5% off. So you could hear how much we were off by. Now, if I reduced the sample size by a factor of 10, it's still unbiased. When I hit enter a bunch of times here, we're still going to get numbers that are fluctuating around 5, which is 50%. But notice, instead of being 1% off and 3% off, and I think the biggest we saw was 15% off, we're right there. That's 10% off, right on the money, 40% off. It took me 3 clicks to get 40% off of what we should have been. And that's not because, again, that's not because the calculator is being biased. That's natural variation kicking in. Sometimes it happens. And I could go the opposite way with it. I could say, you know what? Let's take a sample instead of 100. Let's take a sample of 500. Now we're going to get unbelievably close. All you have to do is figure out how far off of 250 are you? I'm 2 off. And then divide it by 5 to figure out the percentage. So that's 0.4% off. That's 8 off, so that's 1.6% off. That's 6, so 1.2% off. Now we're 7, so 1.4% off. Everybody hear me? Like we're missing the mark still, but we're missing it off by fractions of a percentage now because we're taking so much data that law of large numbers kicks in, and we're getting really close to whatever it is that we're supposed to get. Okay? So pictures 2 and 4, again, that's where you want to be. You have a sampling method that's aimed in the right direction, and hopefully you're on 4 where you can collect a lot of data. Now, the other 2, pictures 1 and 3, they still show the differential between collecting a lot of data, that's picture 1, and not so much data, that's picture 3. But they both represent some biased way of collecting data. For example, just to go back to it, the jelly blubbers in round 2. I told you all months ago, pick 10 of these at random. And a lot of you, in your attempt to be fair, were taking like 10 big and 10 small, or some kind of even split nearly. And what that caused was collectively as a class, we were way overestimating the true average width of these jelly bubblers because there were way more small ones. And what you should have been doing was get like 7 small and only 3 big or something like that. So it wouldn't matter if I told you all just pick 10, or if I told you, you know what, all of you pick 30. It wouldn't matter. Yes, you'd be collecting more data, but you all would have this biased way of collecting data. So you all would be zoning in on the wrong number. Okay. So that's what these 4 images are meant to represent. The 4 combinations of, do you have a biased or unbiased way of collecting data? And are you collecting a lot or a little? Are you getting close or not to the right thing? Or are you getting close or not to something else? Okay. All right. So again, I'd encourage you to read this page on your own time. Go ahead and turn the page. Let me show you a contextual example of applying this idea of bias or not. I find this one, by the way, truly fascinating. It's a true story. You can look up the history of it yourselves at some other time. So how many tanks does the enemy have? During World War II, the Allies captured many German tanks. Each tank had a serial number on it. Allied commanders wanted to know how many tanks the Germans had so that they could allocate their forces appropriately. They sent the serial numbers of the captured tanks to a group of mathematicians in Washington, D.C., and asked for an estimate of the total number of German tanks, N. Here are simulated sampling distributions for 3 statistics that the mathematicians considered, using samples of size 7. The dotted line at N marks the total number of German tanks. So let me be clear. The dotted line that is pre-printed on your paper is something they did not have access to. Okay, that was the right answer. That was the true number of tanks, which they had no way of knowing. What they did was they had a collection of serial numbers from German tanks that had been captured. And what they said was, ideally speaking, these serial numbers should be a random sample of all of the serial numbers that the Germans have on their tanks. So they devised a way of, why don't we take a sample of 7 of the plates that we've collected, okay, and calculate a summary statistic from it. Now, it might have been a mean, or it might have been a maximum, or it might have been an interquartile range, or it might have been a quartile 1. Like, there's lots of different options for what they might analyze. And so what they did was they came up with 3 different statistics. Again, could have been mean, could have been median, could have been mode, whatever it was. And what they did was they ran thousands of simulated samples of 7. Let's take out 7, record the statistic. Take out 7, record the statistic. Take out 7, record the statistic. And they did this thousands of times for all 3 statistics. And these were the resulting distributions. And buried somewhere in here is what they presumed would be the actual number of German tanks. Now, this question would have been impossible for them to answer because, again, they didn't have access to the dotted line. You all do. So do any of these statistics appear to be unbiased? Is biased or unbiased? I would agree. What I'm marking is the center of statistic 2. Okay, and let's be clear, Lena just said it's biased, and I agree with that. The idea of bias is you're not even aiming in the right direction. So I would say whatever statistic 2 was, it was consistently overestimating the true number of tanks. Now, the other 2, I would actually argue, are reasonably centered. Like, that looks to be the center of statistic 1. That looks to be a reasonable center of statistic 3. Does that make sense? So to me, those are the 2 that I would argue are unbiased. Okay, it says, are any of them unbiased? Yes, stats 1 and 3. These distributions seem to be centered close to N. That is the idea. If you have a method that is aiming in the right direction, visually what that should mean is it is centered on the true value. Now, the next question then becomes, okay, if you are part of the Allied forces and you're going to report back to the commanders, okay, this is, or your generals or whoever it is that's hiring you, you're going to report back the number of German tanks you think exist. Well, you have to decide which of these statistics you're going to use to make that estimate. Now, clearly, you're not going to use stat 2. It's biased. It's way overestimating. But the question then becomes, which of the other 2 would you pick? So we have an easy way of knocking out stat 2, but the next question says, which of these statistics do you think is best? Explain your reasoning. So can anyone make an argument between 1 and 3, like which of those is better and why? I would agree with that. I would agree with stat 3, okay? Arnav's talking about the consistency of this prediction. Notice, if you're going to go with stat 1, it's sort of like, all right, well, based on the statistic, they might have as few as these or as many of those. Like there's a huge bandwidth for the number of tanks the Germans might have. But if you go with stat 3, it seems like it's somewhere in here. That's a much more consistent area. So if I'm asked to make a decision here, I'm going to say stat 3, it is unbiased. That proves why it's better than stat 2. And it has less variability. That is why it's better than stat 1. Okay. Remember, when you say unbiased, and now I'm reading the green stuff, even though you all only really need to write the blue, when we say it's unbiased, what we're talking about is the mean of the distribution of sample means appears to be approximately equal to the population mean. Fancy way of saying it's centered in the right spot. Okay. Less variability, the sample means tend to vary less from the true mean. Okay, so you're one of the mathematicians, you've been hired, you come up with this fancy system for figuring out how many tanks the Germans might have. You've settled on stat 3, and yet still there's a pretty big bandwidth for how many German tanks you think there are. There's still a pretty big width there. So that's what question 3 is going to, or part C is going to address. Explain how the Allies could get a more precise estimate of the number of German tanks using the statistic you chose in part 2. So you're going with stat 3, but it still has this big span. So the question is, how do we do this? How do we get it so that there's a more narrow range of how many tanks we think the Germans have? I appreciate it, but I heard from you once already. Anybody? Yep. That's exactly what you should do. Collect more data. Now, I have to admit, I don't know why they were doing samples of 7. My guess is maybe they only had 70 captured German tank serial numbers. And one of our conditions that we're going to talk about is you can't sample more than 10% of the population you have access to. So that might be one of the reasons why they had the very limited sample size of 7. But the bottom line is, I don't know if they could have been taking a larger sample size or just go capture more tanks, wait until more tanks have been captured. Okay. Anything that you have to say that has to deal with larger sample size is what I'd be looking for here. So I said capture more tanks and or increase the sample size beyond 7. With more data, you should get closer and closer to the true value. That's the point. All right, so at the top of the next page, we again have a short chunk of reading that I would say you can do on your own time, but I want to give you all a chunk of time to actually do 7.110 yourselves. Okay, so let me zoom in on this real quick. Again, I'm not going to read through the example. Right here, just to make sure people are clear on the context, it says for quality control, workers at a battery factory regularly select random samples of batteries to estimate the mean lifetime. Here is a simulated sampling distribution of the sample mean lifetime in hours for 1,000 simple random samples of size 100 from a population of AAA batteries. So let's just be clear. This display is meant to represent 1,000 dots. Okay. There's so many dots, like maybe that's just one dot and maybe those are just 2 dots, but this column is so many dots that you can't even see the individual dots. Okay. Now, keep in mind also what each of these dots represents. Bless you. They represent the average lifespan that was observed in a simulated random sample of 100 AAA batteries. So if you get 100 AAA batteries and they're observed to have an average lifetime of 48 hours, that's one of those dots right there. If they had an average lifetime of 59.5 hours, that's that dot right there. Okay, and it seems like a ton of the samples ended up with average lifespans of around 53 hours. That's what this is saying. Okay, so make sure that you can appreciate that technically speaking, this display is showing you the results obtained from 100,000 simulated batteries because it's 1,000 samples and each sample involved 100 batteries. Okay, take 5 minutes, see if you can complete this question yourselves, folks. Go. Also, as a side challenge, if there's anyone fast enough, because I don't know how much time 5 is, I had a separate question I wish I had included if you want to try to process that as well. All right, students were given the remainder of the period to complete 7.110 for the purpose of completing the recording. I'll reveal my answer key now. Part C, again, is a question that I sort of invented on my own because I thought it provided a little more variety compared to the 2 questions that preceded it. Thanks for watching. Have a good one.